Welcome to part 2 of the introductory lecture on base R programming for core empirical research methods at the University of Oxford. In this part, we're going to talk about R's most basic data type, atomic vectors. And when I say data type, of course, I am making a mistake. In our last segment, we talked about data types. Vectors are not data types, vectors are a data structure, and that's actually a pretty important distinction. So an atomic vector is one-dimensional, and it stores data of a single type. So this is a structure. This is a kind of a box, if you will, that contains stuff. The stuff is all of a particular type. If you'd like to learn more about atomic vectors, there's tons of detail in Chapter 3 from Advanced R. You can click on this link from the lecture notes, I should say the lecture slides on the course website. And remember from the previous segment that the key types in R for our purposes are double, integer, character, and logical. So we're going to be looking at atomic vectors that contain each of these types. The first R command that we need to know for working with atomic vectors is C. This function means concatenate. In other words, string together or chain together. It can be used to create an atomic vector. Now we've already seen type of. This can be used to find out the type of something in R, and that includes an atomic vector. Atomic vectors are one-dimensional vectors. Just like vectors in mathematics, there's a list of things. Length tells us how many things there are. And here are some simple examples. First, I have x gets c 2.3 minus 1.7, 5, 0, 6.2, and 7. And notice that to create this atomic vector x, I'm separating numbers here by commas inside of the concatenate command C. Similarly, I can form this atomic vector y, which contains character data and a really important message about the course you're currently taking. Finally, z is an atomic vector that contains logical data. I can use the length command to find out that there are indeed 6 things inside of x, 6 elements, whereas there are 4 inside of y and there are 3 inside of z. The type of x is double. It contains R's default numeric type. The type of y is character, and the type of z, it might not come as a surprise, is logical. Here's a little exercise for you. You should pause the video at this point, think about the exercise, check your work against the solutions on the course website, and then resume watching the rest of this video. The next thing we need to know about atomic vectors is how to access their elements. We do this using brackets, square brackets. There are various ways that we can subset a vector using these square brackets. The first way is with a single index. So x bracket 2 would give us the second element of x. We can also supply another vector inside of these brackets. So here I am going to subset the vector x with another vector, 2, 5, 7. What that would do is it would return the second, fifth, and seventh elements of x. A third way that we can subset a vector is by using a logical vector of the same length. So as you can see in my previous example with x brackets c 2, 5, 7, well, there I extracted 3 elements of x, and it wasn't necessary that that x has only 3 elements. As you can see by the statement I've made, 2, 5, 7, I'm implicitly assuming that there's at least 7 elements inside of x. But if you want to use a logical vector to subset x, then it needs to be the same length as x. In this case, you would supply a bunch of true and false values, where a true means keep that element of x, and a false means don't keep that element of x when you're deciding what to return. Negative indices are also allowed in R, but what they do is remove elements. So x bracket minus 1 is x with its first element removed. And you're also allowed to use repeated indices. This can actually come in handy. One thing to be aware of if you're coming from other programming languages is that R, like Julia, indexes vectors from 1, following the convention that's used in mathematics. In contrast, Python, C, C++, and many other programming languages actually index vectors from 0. It's annoying that there are different conventions, but you'll get used to it in no time if you just think about R as being more similar to the math way of doing things, and you think about Python and C as being more of a computer science way of doing things. Here are a few simple examples. Here I've got an atomic vector y that contains character type, and I'm going to pull out the first element. I could also pull out the first and the fourth element. Well, I could also pull out the third or rather the second and the fourth element by subsetting y with this logical vector false, true, false, true. And I could even pull out everything but the first and fourth element by writing y brackets minus c 1 comma 4. So what's happening there is c of 1 comma 4 is just the vector 1, 4. Putting a minus in front of it tells R, hey, get rid of elements 1 and 4. So all we're left with are elements 2 and 3. Similarly, we could just get rid of one element, the third one. That would be y brackets minus 3. And there are many more possibilities, all of them pretty boring. I'll just draw your attention to the last one. Here I'm using repeated indices, and I can repeat as many indices as many times as I like. Have you noticed that every time you get a result in R at the R console, there's this little 1 in brackets? So if you type 2 to the 8th, you're not going to see 256. You're going to see bracket 1 bracket space 256. Well, what is that? It turns out that R doesn't actually have scalars. There is no such thing as a scalar in R. There's only vectors of length 1. So that 2 to the 8th right there is actually a vector of length 1. You can see that if you assign 2 to the 8th to the name W. So here, if I take length of W, I will see 1. Now, I can also create vectors that have more elements than 1, of course. There's a handy shortcut in R, which is the colon. So if you assign R gets 30 colon 70, that's actually shorthand for creating the vector 30, comma 31, dot, 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 69, comma 70. And you can see that if I ask R to display this amusingly named vector R, wow, I wasn't feeling very creative when I made this slide, then it's going to print out that little 1 in brackets, lots and lots and lots of numbers, then it's going to reach the end of what it can display on that line of your screen, and then you're going to see in brackets something else. Here it's 26. That's because it had to wrap the line somewhere. It had to break the line to display the next number, because otherwise there wouldn't have been any space on your screen. And when it did that, it had reached the 26th element of the vector. So when R prints these little things in brackets in the console, it's trying to tell you, roughly speaking, where you are inside of the vector that it's displaying. Now we have another exercise for you. So please pause the video, attempt the exercise, and check your work before continuing. One of the best features about R is that we can do math with vectors. In other words, all mathematical operations in R are designed to operate on vectors. The way that they work is element by element. So let's take a look at a few examples. Here I'm creating a vector x, which contains 5, 6, 7, 8, 9, and another vector y, which contains 0, 1, 2, 3, 4. I can add x and y, and if I do that, I'm getting the usual vector operation that you know and love from mathematics. So 5 is added to 0, 6 is added to 1, 7 is added to 2, 8 to 3, and 9 to 4. Similarly with subtraction, x minus y gives us 5, 5, 5, 5, 5. Because all we're really doing is adding x to negative y. Multiplication is also element-wise. So x times y with this asterisk is not matrix multiplication. It is not the dot product. It is not the cross product. It is element-wise multiplication. So 5 is being multiplied by 0, 6 by 1, 7 by 2, 8 by 3, and 9 by 4. The same goes for division. We can do y divided by x. And we can even raise x to the power y, which can be very convenient sometimes. So here we're taking 5 to the power 0, 6 to the power 1, and so on. Another convenient thing about R is that practically every function is vectorized. In other words, practically every function accepts a vector as an input. Here are some handy functions that you may find helpful. Sum computes the sum of a vector. Prod computes the product. Absolute value computes the absolute value. ABS of all the elements of a vector. Again, it's element-wise. Square root, SQRT, computes the positive square root. Again, element-wise. Now, min is computing the minimum of all the elements in the vector. So obviously for min, it doesn't really make sense to think about an element-wise minimum because there's only one element in each element, so there'd be nothing to compare to. And the same goes for max. Relational and logical operators are also vectorized. Here are just a few simple examples. We can compare x to y, and we're then comparing 1 to minus 1, 2 to 3, 3 to 2, and 4 to 6. So we see that 1 is indeed bigger than minus 1, 2 is not bigger than 3, and so on. The same is true for all of our favorite logical operators. Here we have an example with z and w. Z or w proceeds element by element. Same is true for and. Now, you may occasionally want some different behavior out of R. You may not want to compare every element one by one. You may want to check if any element meets a certain condition. Well, you can do that. There's a function called any. So this function returns true if any element of its input is true. So if you remember from up top where we compared x to y, it was indeed the case that at least one element of the vector x greater than y was true. So any x greater than y returns true. All, on the other hand, checks if all the elements are true. And since it wasn't the case that every single element of x was bigger than y, this returns false. Recycling may be good for the environment, but in R, it can be confusing and sometimes even a little dangerous. So what on earth is recycling? Well, let's take this innocuous-looking expression at the top of the slide. X gets minus 2 to 2, which again is shorthand for the vector minus 2, minus 1, 0, 1, 2. You might think to yourself, boy, I'd really like to add 3 to every one of these elements. And I should just point out that this lecture is pretty boring. Future lectures aren't going to be so boring, but we've got to get through this stuff before we can get to the more interesting stuff. Anyway, back to x plus 3. You may think, wow, I'd really love to add 3 to every single one of these elements, but I don't want to set up a vector of 3 over and over. I don't want to have to construct 3, 3, 3, 3, 3 just to do my addition. And don't worry, R's got you covered. You can just type x plus 3, and it does the right thing. What is it doing? It's actually recycling that value 3. It's using it again every time that it carries out an addition. The same works for subtraction, and the same works for multiplication and division. So when we see here 2 times x, this is really scalar times vector multiplication as in mathematics. So every single one of those elements is multiplied by 2. We can also raise the vector x to the power 3. And again, that 3 gets recycled. So we raise every single element of the vector x to that power 3. It's convenient, and the examples that I have on this slide are the kind of thing that you're going to see in our code every day. So to understand how recycling works, there's a couple of rules that we have to bear in mind. First of all, if any vector has length 0, the result will 2. Now, up until now, we haven't seen any vectors that have length 0. They're not very interesting, but let me create one for you. This is a command that will create a vector of length 0. And if I display it, so I say x gets numeric of length equals 0, then I type x, I'm going to see numeric of 0, which is an empty vector. It has no elements. If I run the command length of x, I will get 0. Okay, so now let's try to add x, which has no length, remember, it doesn't contain anything, to -2 to 2, which is a vector that does contain things. In particular, it contains -2, -1, 0, 1, 2. This returns numeric 0. In other words, a 0-length vector. That's the first rule. The second rule is that if you don't have 0-length vectors, then the length of the result will always equal the length of the longer vector. So again, as long as none of the vectors you're working with has length 0, then the result of recycling is always going to equal the length of the longer vector. So let's take a look at this baffling statement. C1, 2, so that's the vector 1, 2, is being added to a vector that actually has 4 elements, not 2. The vectors 5, 6, 7, 8. So what on earth is happening here? Well, by our second rule of recycling, the length of the result has to equal the length of the longer vector, so it has to equal 4 in length. And indeed, we see that the result at the bottom of the slide contains exactly 4 elements. So this command is actually equal to 1 plus 5 is 6, 2 plus 6 is 8, 1 plus 7 is 8, and 2 plus 8 is 10. In other words, that first vector, 1, 2, is just repeated in order to pad out the length of the thing before the plus sign, the thing to the left of the plus sign, so that the dimensions match. So 1, 2 has been recycled. Now, recycling can be very convenient sometimes, but it can also be dangerous. R will warn you if the length of the longer vector in your statement isn't a multiple of the length of the shorter one. So on the previous slide, I added 2 vectors together where one of them had length 4 and the other had length 2. So R did not warn me. It just silently duplicated the first 2 elements of that initial vector of length 2 in order to make the addition work out. But if I instead try to work with 2 vectors such that the longer one is not a multiple of the length of the shorter, R will warn me. So let's see what's going on here. When I try to add 1, 2, 3 to 5, 6, 7, 8, this is equivalent to 1 plus 5, 2 plus 6, 3 plus 7. Oh, now what am I going to add to 8? Well, R recycles, so it goes back to the beginning of the vector 1, 2, 3. And it says, hey, there's a 1 there. Why don't I use that? So the final element in this resulting vector is actually going to be 1 plus 8. In other words, 9. My advice to you is to avoid recycling, except in the scalar with vectors case, which we looked at a couple slides back. So things like 2 plus x, or 2 times x, or x to the 4, that's all fine. I would suggest that you avoid anything that looks like what I've got on this slide, unless you really know what you're doing. It's possible to use recycling in R to write some very slick code that runs fast, but usually the real bottleneck is not the speed with which our code runs, It's the errors that our future self has to try to sort out because our past self wasn't very considerate and did things that were too confusing. That's unfortunately a theme that's going to come back and back in this course and in your life if you spend as much of it writing code as I do. And now we have another exercise for you to pause and ponder. Again, you can check the answer to this exercise on the course website. Sometimes we want to replace the elements of a vector. We can do this very easily in R, and here's how it works. Broadly speaking, on the left-hand side of our statement, we're going to describe the values that we want to modify. On the right-hand side, we're going to use the gets assignment operator to overwrite whatever is on the left-hand side. So here's a little example. I will construct the vector x, which contains values 1, 3, 7, 8, and minus 4. Now I am going to describe what I want to modify. X bracket 4 refers to the fourth element of x. So here I've written x bracket 4 gets 5. Let me display the result. I'm going to type in x, and as you can see, the result is 1, 3, 7, 5, negative 4. So I've actually replaced that fourth element of x with a new value. So one way to describe the values that you want to modify is just to use a bracket to refer to a particular element of a vector. Another way is to put a logical vector inside of the brackets. So this one's going to look pretty strange if you've never seen something like it before. I have x bracket x less than 0. So let's read it from inside out. Inside the brackets, we have x less than 0. That's a logical vector of the same length as x. What's going on here? Well, it's recycling. When we do the comparison of x with 0, we are comparing every single element of x with 0. So we're comparing 1 with 0, 3 with 0, 7 with 0, 8 with 0, and minus 4 with 0. X less than 0 will return true whenever a particular element of x is less than 0. So the first, second, third, and fourth elements are going to be false, but that final element, the fifth one, is going to be true because indeed minus 4 is less than 0. So in this statement, x bracket x less than 0 gets NA. What I'm doing is I'm assigning the value NA, which remember means missing, stands for not available, to whichever elements of x are less than 0. And because that's only the final element of x, what's happened here is I get a result of 1, 3, 7, 5, NA. So I've replaced that fifth value with a missing. And in fact, we can use all of our favorite ways of subsetting vectors to replace elements. So here I'm going to explicitly specify elements 1 and 3 inside of the brackets, and I'm going to replace them with minus 4 and 7. So I can simultaneously assign multiple values to multiple values, as I've done in this case. So you can see here, the first element of x used to be 1. I've now changed it to minus 4. And similarly, the third element of x, well, actually, that started out as 7, and I've replaced it with 7, which doesn't look very interesting, but that's fine. Sometimes it can be really helpful to give things names. This is not only useful because we can refer to things by names, but it's also useful because it's going to change the output that R prints to make things easier to read. So let me show you how you can name the elements of a vector. There are several methods. The first method is to create your vector and then use the function names to assign it a vector of character data. So here I made a vector Frank, and it's a little bit out of date now that I'm slightly older than that. But the vector is 1983, 40, and 1. Now I'm going to give this vector names. So I say names parentheses Frank, gets, C, birth year, comma, age, comma, number siblings. And now when I type in Frank, I'm still going to see the vector 1983, 40, and 1, but I have some helpful labels at the top, some helpful names. Now, there's another method for naming a vector, and that is that you can name it when you're creating it. This can be helpful sometimes when you're writing code, say to carry out a simulation study, and you want to make sure that the simulation prints out a label on everything that it returns. So here I can create the vector Frank, and inside of this concatenate command, I put in quotes birth year equals 1983, age in quotes equals 40, and number siblings in quotes equals 1. That's going to do exactly the same thing as with names. You can also use names to print out the names of a vector, which I don't actually show on this slide for some reason, or to rename. So what I'm now going to do is I'm going to change the third element of the vector Frank to be 0, and I'm going to change the name associated with that element to be number of Nobel Prizes, because unfortunately, I have only accumulated 0 Nobel Prizes thus far. Another nice thing about naming elements of a vector, besides improving the way that things print out so they're easier to read, is that we can now access elements by name. Now you may say, why does this matter? If I know that age is the second element of the vector, I can always access it more quickly by just typing Frank bracket 2. But in fact, referring to things by their names can be pretty helpful because you no longer have to know exactly where in the vector something is. You can just know what it's called. And if the names don't change when things are sorted, this can be really handy because if for whatever reason this vector got scrambled such that age became the first element, trying to access it by position wouldn't have worked. In other words, Frank of 2 would not have returned the same thing, but trying to access it by name would. The way that we do this is we take the vector, brackets, and then we put the quotes inside of the inside of the bracket to refer to that element. So here we can pull out my birth year, and we can also pull out repeated elements if we want. We can pass a vector of names to Frank. Now, if you try to access an element that is not contained in the vector, you will get NAs. And I'm not telling you my salary or my zodiac sign. We've talked about logical operators. We've talked about comparison operators. So now it's time for us to talk about set operations. R actually has a full set of functions for dealing with sets. The keyword null in all caps is how we denote the empty set in R. You can actually assign something to be the empty set. For example, X gets null. Union is union of A and B. Intersection is intersect A comma B. Set difference, which in mathematics is sometimes denoted by this slash, A slash B, or sometimes by a minus B, although the way I prefer to write it is A intersect B complement. You can do set difference in R, however you prefer to think of it in mathematical notation, by writing set diff A comma B. You can also test for equality of sets. So set equal A comma B returns true if and only if A is a subset of B and B is a subset of A. Now here's an interesting and slightly terrifying looking object. Percent in percent. What is this? Well, you're going to be seeing words wrapped inside of percents at several points in this course. When you see them, don't panic. Think of it just like an operator. So think of it like multiplies or add or subtract. So it's just like another operator that works on two objects, one to the left and one to the right. A in B returns a vector with the same length of A, and this is a logical vector. So it contains a true for every element of A that is contained in B, and a false otherwise. If you're thinking, why would I ever want this? Well, just wait and see. In can be very, very helpful in programming in R. As usual, we'll take a look at a few examples. So here I'm going to set up A, which is a vector, 1 to 5. To be clear, there's not really a set type in R. So we have set operations, but we don't really have sets. So when we do set operations in R is treating the vector as though it were a set. In other words, all of these operations ignore the order because a set is an unordered collection. So here I have A, B, and C. The union of A and B is just 1, 2, 3, 4, 5, 6, 7. Now notice that there were some repeated elements there. A contained 1 to 3, and actually 3 was, I should say A contained 3 to 5, and 3 to 5 was also contained in B. When we take the union, however, we're not going to get those duplicates. We could also take the union of A with C. If you take the union of any set with the empty set, well, you're just left with the set you started with. Similarly, we could intersect A and B. We could find out what elements they have in common. The answer is 3, 4, and 5. We could intersect A with C. If you intersect any set with the empty set, you get the empty set because there are no elements in common between A and the empty set. Set difference tells us everything that is in A that is not in B, and those elements are 1 and 2. Set equal, A and B, returns false because A and B are not equal. There are some elements that are in A that are not in B. Finally, A in B returns a vector of the same length as A, 5 elements, and it's going to check for each of those elements whether it is contained in B or not. So first we check 1. Is 1 contained in B? No. So we return false. Next we check 2. Is 2 contained in B? No. So again, false. What about 3? Yep, 3 is in B, so we return true. And the same is true for 4 and 5. Coercion sounds like a bad word, whereas recycling sounded like a good word. But in R, coercion doesn't mean that you're trying to force someone to do something against their will. It's just a way of changing the type of something. So remember that in R, an atomic vector stores elements of a single type. If you try to put multiple different types inside of an atomic vector, R is going to convert some of the types to make sure that everything is indeed of the same type. Otherwise, it can't store the result in a vector. This is called coercion. So R is going to coerce everything to be of the same type. The key rule that you need to know for coercion is called precedence. And the basic idea here is that character gets higher precedence than numeric, gets higher precedence than logical. The highest precedence type wins, and everything else is coerced. So here's an example. I've got a vector x, which I try to create such that it will contain the numeric 1, the logical true, and the character quote 1. And indeed, 1 and quote 1 are not the same thing in R. This is crucial. One of them is the number 1, and the other one of them is the character 1. And I just realized that I just said 1 about a dozen times. So what happens? Well, in the end, we don't get a numeric vector. We don't get a logical vector. The reason is that those two types have lower precedence. We get a character vector. Roughly speaking, the idea here is to try to preserve as much information as possible. Basically, anything that you type into your computer can be represented as character. That is not the case for numeric, and that is not the case for logical. You cannot represent anything at all by turning it into numbers. There's going to be some information loss if we tried to convert the word precedence into numbers. So what R is doing is it's trying to avoid information loss. You can also coerce manually. So if you wanted to force something to become a character type, you could use as.character. Similarly, to coerce to numeric, you can use as.numeric, and for logical, as.logical. Here's a few examples of coercion. In the first one, y is a vector that I try to set up so that it will contain both logical and numeric types, but that's not allowed. We can only have a single type. So because numeric types have higher precedence, true is coerced. And true is coerced to 1. That's actually really helpful to know. In R, true will be coerced to 1, and false will be coerced to 0. You can actually use that to your advantage when you're programming, because sometimes you want to move back and forth between a numerical representation of true and false, 0, 1, and a strictly logical one with the words true, false. Here I'm going to try to coerce the character vector, or rather, I'm going to coerce the numeric vector 1, 2, 3, 4, 5, such that it will become character vector, as dot character will do the trick. And then, somewhat pointlessly, I could coerce things back. So here's an example where I create character vector quote 1, quote 2, quote 3, and I convert back to numeric. I mentioned a moment ago that it can be very handy to use the coercion rules for logical values. So here's a vector of true, false, true. You might wonder what would happen if I computed sum. Well, the trues are treated as 1s, and the false is treated as a 0. So we get 2. Similarly, when we take the product, we're going to get 0. Both of these can come in handy. So a product of a logical vector is really the same thing as all. It returns, except that it's going to return a 0 and 1 rather than a true and a false. And now we have an exercise. This one is particularly fun because it involves one of my favorite card games. So if you are not familiar with the game of Scopa, I recommend that you take a peek at these links that I provided on the slide. If you're not interested in the game, that's disappointing, but you can still solve the exercise without it. So take some time, think through this exercise, and then when you're done, you can check your work with the solutions on the course website.